So I am going to discuss how to derive the formula for conic sections. We will start with a short introduction on what a conic section is and proceed with the derivation of the equation of each conic section. So what is a conic section? Huh? Conic section. When we say section, it is the intersection of a solid and a plane. For example, we have a we have a cube. If we intersect it with plane, say this plane, then the section that is formed would be this, which is of course a square. So for a conic section, it will be the intersection of a cone and a plane. So a cone, as defined, is generated by a line where a point is fixed and following a directrix, say this figure. So that if we are to generate the cone, say like this, like that, can you imagine? Like that, we will be able to form this geometric figure like that, like this. Of course, the generating geometric figure is a line, so all these can be extended to infinity like this. This is a what? This is a conic surface. A cone is formed out of the conic surface if we are to take this part together with this plane, which will serve as the base of the cone. If we are to consider the two naps like that, some books would call it a double cone. And so again, what is a conic section? It is the intersection of the cone like this and a plane, depending on how the section is formed. When the cutting plane is perpendicular to the axis, what do we mean by axis? Axis is a line through the vertex passing through or intersecting the center of the base. If the base has a center, but more or less, that's the idea of the axis. So if the cutting plane is perpendicular to the axis like this is the cutting plane, what is the section formed? Well, the section formed is actually it's not very clear because my drawing is not great, but we will be able to form a circle like that. If the cutting plane is parallel to a generator, generator. So how is it formed? Well, like like this, like that, no? Parallel to this generator, then what is formed is a parabola. Parabola. This is a circle. This is a circle. If the cutting plane is in any angle, but the angle is acute with respect to the axis, like this, for example. So what is formed is an ellipse, like that. And if the cutting plane is parallel to the axis, like this, parallel to the axis, no? What we form is a hyperbola. No? So, in what other positions can we place the cutting plane so that we can cut the cone into something where we can obtain a section which we call a conic section? So far, there are only 4, but technically there are only 3 because a circle is considered as a specialized ellipse. Why a specialized ellipse? We will explain in a while. Now, these are geometric figures. And conic section is a topic of analytic geometry. Analytic geometry is the marriage between geometry and algebra, so that the geometry that we are used to in our geometry classes, which of course pictured with geometric figures like squares, rectangles, lines, points, etc., they would have an algebraic representation in analytic geometry. In other words, these geometric figures would have their corresponding equations. How do we come up with these equations? That is what we're going to do today. So we will start with the first conic, which is the parabola. So how is a parabola defined? A parabola is formed with or through a line and a point. How is that? If we have a moving point, that is, say, this point, let's call that point P, which is equidistant from the fixed point and the fixed line, equidistant. So that if it will move, because we said that the blue point is a moving point, if it moves in such a manner that it maintains that ratio of equality of distance, of course that point can't go up, because if it will go up, the distance between that point and the line and its distance from that point to the fixed point wouldn't be equal anymore. So where will it go? It has to go towards the right direction. So somewhere here. So that this distance would still be equal to this. So the moving point is already here. It's moving, so maybe the next time it's there. Sorry. Like that. Like that. So, if we are to follow its path, this is now the path of the moving point. Path of the moving point. The path of the moving point is how we define a locus. How we define a locus. So of course, it's not only going to that direction only. It can also go to this direction. And this is how we form a parabola. This is how we form a parabola. So, what is now its equation? Now, the equation comes up if we are to sketch that locus on the xy plane. So, we have this. If this is our xy plane, this is x, this is y, no? You can place that parabola anywhere, except that to simplify our life, we will start with coinciding this point with the origin here. Let the fixed point be somewhere here. This is, let's call that F. Why do I call that F? Later we will know. And the fixed line here, which we call, say, D. Why D? Well, I now tell you F because that point is actually called the focus of the parabola. Why D? Because this line is called the directrix. And our parabola would be this. No? We said that it moves equidistant. So the distance between the moving point P, that would be PF, is equal to its distance from PD. PD. Like that. No? So, if that is the distance and we take its ratio, we divide both sides by, say, PD or PF, doesn't matter, no? Then we'll get what? PF over PD, since they're equal, is equal to 1. And this ratio is called the eccentricity, which is usually represented by E. So now, what do we know? We know that a parabola has a focus, has a directrix, and has an eccentricity. Now, this extreme point of the parabola, that extreme point is called the vertex of the parabola. The vertex of the parabola. So, if we are to have this relationship between a moving point, a fixed point called the focus, and a fixed line called the directrix, depending on the movement or the path of the moving point P, the ratio would either be equal to 1, in which case the eccentricity is 1, we'll get a parabola,